Hello everyone, welcome to this tutorial. My name is Emerson Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to do water storage mapping in the Google Earth Engine platform using Grace dataset. At the end of this tutorial, you will be able to produce the water storage anomaly map for your region of interest with the high quality using the Grace data. This tutorial is really useful for those of you who are interested to the hydrological analysis and water resources studies. So, make a new notebook in the Colab in the first step. Then we need to import necessary libraries to deal with Google Earth Engine platform in the Python API programming. Let's start with EE and GEE map. These are essential libraries. Then we need Xarray libraries and we need to install the XEE library. The XEE is one of the newest libraries developed by the Google community and allowing us to integrate Google Earth Engine and Xarray data structure that help us to apply machine learning algorithm in Python on the Google Earth Engine data catalog. So, once the importing process done, clear the selected output and make a new cell. Now we need to establish a connection between Earth Engine and Colab environment. Earth Engine authentication, first authenticate and initialize. So we need to initialize the Earth Engine account on Earth Engine account. Enter your account ID. Go to the code editor environment, upper right, there is an option, then project info. You can find your cloud project ID. Paste it into the project. The next argument is the OPT URL. If you search on the net about the Earth Engine and Xarray, you will find a GitHub page, a detailed instruction about XEE library. A bit scroll down and here you can find the OPT URL address. Paste it. Run the cell. After a few moments, the Colab asking you permission to access to your account. Select the associated account and click on continue again. Okay, now connection established, meaning that from now on you can use Earth Engine capabilities in the Python and even you can call the Earth Engine libraries here. So, in the first step, before further analysis, I need to define the region of interest. Create a library, create a variable map sets to from GEE map, call the map function with the satellite base map, just like this. Let's run the map and after a few moments you will have a user interface where you can select your region of interest. So, to define the region of interest, I suppose to use large scale international boundary polygon simplified version. So, first I need to choose my region of interest. I prefer to work on my own country, Iran, to show you how water storage varies from one year to another year in this area. Iran located in the arid and semi-arid region and over the last years highly suffered from the water deficiency. So now I'm gonna find a way to select the Iran polygon here. So the easiest way is select the area by a marker. So in the next step, I can call this polygon and filter it based on the marker, but we need to have a marker as a shapefile. So the location sets to from the map, select the last feature, convert it into a geometry, print the lock, and you have a point as a shapefile layer here. So now we have the Earth Engine feature collection showing the country's boundaries. So for example, a new variable, Iran created, make a tuple, paste the feature collection. So filter the collection based on a marker or location, and then convert it into a geometry. Let's print Iran. After a few moments, you will have a multi-polygon. So there is a multi-polygon here, but before conversion to a geometry, you can check the layer property. If you go to the feature, only one feature selected, and here you can see the country name is Iran. So the region of interest selected successfully. I want to actually plot the Iran's border on the map. It is really easy to do. Back to the geometry formats, use the map dot, add layer. So I want to visualize Iran, and layer name should be Iran, just like that. After a few moments, you can see the whole of region of interest without any challenge, like a piece of a cake. So now in the next step, I need to call the grace dataset for this area. So if you go to the Earth Engine data catalog, you will find this product, Grace monthly mask grid version, global mascon, CRI filtered, available from 2002 to the present. The spatial resolution is 50 km, but original resolution is 300 km. It's only resampled to the 500 to 50 km. So the Grace product shows the water storage through the LWE thickness with the centimeter unit. So let's call it into the code by Earth Engine snippet, Grace dataset, or I call it an image collection. It is easier to call. So select the target band. It is LWE thickness. Let me copy the band name just like this. There is no scale factor, and that's what we have. It has a monthly frequency. Print the collection first. As you can see, 238 elements available through the time. You can see the feature collection structure. We have some properties and also a single band selected. This structure belongs to Earth Engine image collection format. From now on, we can bring this data, bring this collection out from Earth Engine, and we want to convert it into a multi-dimensional array structure thanks to X-array and XEE. So it is the best step because from now on we can use the Earth Engine datasets as an import for numerous models and applications available on Python, and we have access to a large amount of algorithm here that they didn't available, that it's not available in the Earth Engine JavaScript environment. So a new dataset will be created like this from X-array library, called the open data set. Import the collection, convert it to XEE to Xarray according to EE engine. CRS EPSG4326. This is a unique ID utilized for WGS84 and it is unique for all around the world. Region of interest should be Iran. Remember that you need to clip your dataset in the Earth engine based on a shapefile border. So make a loop structure, call a function, and the input to the function, consider it as IMG. I want to clip each input image based on Iran's border, and I want to have the property of inputs. Let's copy properties of input images should be copied to the output property names. Let's run. After a few moments, the process is done. Still we have same amount of data, but they are clipped based on region of interest. Okay, now back to the data set. The scale size is very important. So as I said, the inherent resolution is 300 kilometer. So it doesn't matter you add, for example, 100 kilometer or 50 kilometer as a scale. Originally, the scale of information is based on 300 kilometer. The scale here is based on a degree. 1 degree means 100 kilometer, or 2 means 200 kilometer. I choose the 100 kilometer. So let's run. Now we are converting an image collection into a multidimensional structure. As you can see here, we have a multidimensional structure. What does it mean? Meaning that we have a variable LWE thickness that shows the water storage anomalies, and this information or this data available in 3 dimensions through the time, longitude, and latitude. We have an array structure here, and we now we have a different structure in our data set that is completely matched to be used for the machine learning or data science analysis. So in order to avoid some sort of potential problems in the next step, I always recommend to sort the database, sort by, based on temporal information. Sometimes if we didn't do this, we may face with some sort of problems in the next step. That's why I always suggest users to apply sorting just after conversion from Earth Engine to Xarray. So if you do a very simple multiplication, like for example multiply to 1, it is also useful because making a new data set separated from the original data set, and nothing will be changed in the new data set. Just we are making a new data set separated from the previous one that help us to increase the speed of processing. It's like a kind of trip. There is no scientific reason behind it. Just a trick in the programming, at least in the Colab environment, typically I use to speed up the processing in the next step. For some of the data set, it's very useful, but sometimes no, it doesn't matter you do it or not. But most of the time, I prefer to apply it. Nothing will be changed, just you will have a new data set separated from the previous one. So that's it. Okay, Now the data set is same, and just we did this process to actually speed up processing and avoid some sort of misorder problem in the temporal frequency. So what's the next? Now I have monthly water storage. First of all, I want to calculate the average of each month through the years to see what is the water storage situation based on monthly behavior. So here we will have a DS months. So let's group the data sets based on month format. From time, we have a time uh, dimension, and we can get the month from the time information. Then calculate the average of each month through the time. That's really easy. So let's make a print, and as you can see, and as it is expected, we have 12 image here, one average image per each month. So let's do the visualization. So to see how water storage dynamic changes from one month to another month. So DS months, select the variable, LWE thickness is the variable name. Make a plot. Plot has different axes. X-axis sets to longitude dimension. Y-axis latitude dimension. Call axis sets to here the temporal dimension. Here is months. And robust help us to increase the quality of visualization. Should be true. And what's the next? For example, here call wrap. How, as we wanna, as you know, here we are making a multi-temporal plots. It is important to know how many map we should have per each row. For example, I want to have 4 map in each row. So let's run. As you can see, the quality of the output is very low, and it's very hard to interpret and extract useful information. That's why I'm suggesting to do some sort of changes, because visualization is one of the important steps in the remote sensing data analysis, because it helps us to extract more useful information. First of all, change the CMap to the turbo style. For example, if you search about the CMap and Python, you can see the visual perspective of each color palette available in the Python. So, and I prefer to change the plot style to the contour view for this dataset. In some cases, the contour view is very useful for mapping. In this case, for example, the spatial resolution is really coarse, and it is hardly understand what's going on in the region. But contour F actually give us a smoothness situation. Let's run. Now everything changed. Now we have a smooth output and easier for interpretation. You can also increase the levels. If the levels not enough for the interpretation, you can increase it. Levels sets to 20. That causes more classes and easier for interpretation. Okay, now we have a better visual perspective. From January to December, red colors negative values and blue colors positive values. The grays shows how much each region gaining the water or how much losing the water. Losing water highlighted by for example, the red colors, and gaining water highlighted by blue colors. As you can see, in the summertime, in the winter time, mostly we are gaining, but in the summertime, because of the low precipitation and higher evapotranspiration, we more losing in these times. So that's actually a kind of pattern or monthly pattern or monthly behavior of the gaining and losing the water storage. So let me show you another example in which we want to monitor the monthly water, the annual water storage over the 2 years, 20 years, for example. So we already have the data sets, the monthly data set here. I want to convert it into the annual format. So there it is. The DS annual. Get the DS first and resample it into yearly format where for each year I want to calculate the average. DS annual. So something is wrong here. ds.resample cannot reduce dimension. Oh, sorry. Mean over time. That was my fault. Okay. Now we have 23 years an average water storage through the time. So I forgot to set a filter date here. It is better to add a filter date, for example, from 2003 to 2024. I'm making this video in 2025, so and the dataset is available from mid of 2002. That's why I prefer to select those years in which whole of the months are available. So after the collection updated, we need to run each cells again to update our result based on. Not a serious change in the output, but we need to do it for the annual resampling now. The code example is also available below this video on my YouTube channel, and feel free to use that example to actually fix your issues or challenges in the coding process. So as you can see, 21 years data now is available, and I want to actually make a same plot, but this time for the annual data sets. So get the annual data set first, just like this. Select the target band or variable LWE thickness and make a plot with the contour format, contour F. So x-axis longitude dimension, y latitude dimension, call temporal dimension here. This is no longer monthly. Here we have annually, so the time explaining the temporal dynamics. So the next one, the next argument, cmap turbo R, robust sets to true, and call wrap, for example, is 5. Let's run a code. So as you can see here, let me to increase the levels to 20. There it is. So as you can see here, we have annual water storage data set starting from 2003 to 2023. So the bluish color actually showing how much water gains based on centimeter, and the darker areas or reddish area showing how much water loses through the time based on centimeter. As you can see, in the early 2000s, we are experiencing uh, a stable situation or somehow gaining water through the time. So, but as we go further and close to the recent years, you can see that the reddish pattern increasing, meaning that we are losing more water more than gaining water. We are losing water storage through the time, and in some areas we are losing 36 centimeter per year. That is too much. So now it's a good example about the GRACE applications. Okay, in the next step, I'm gonna show you how to produce the GRACE anomalies through the time. So, what anomaly means? I want to get an average for the whole of the time and see how much we are gaining or losing the water compared to the long-term average. So that's interesting uh, step in this tutorial. So let's calculate the average first. ds mean time. This is the average, very easy to do. Then anomaly. So sets to call each dataset first minus the long-term average. Remember to do this for the annual data. So ds annual average and ds annual subtraction with the average, just like this. Let's run. We will have the same amount of the data sets here. So from 2003 to 2023. So now I wanna select LWE thickness, the variable, make a plot based on contour style. X sets to longitude, Y sets to latitude, call sets to time, call wrap sets to, for example, 5, robust true, and cmap turbo R and levels 20, for example. So let's run the anomaly image. So now we have more information. The positive values showing that how much we are gaining more compared to the long-term average. From 2003 to 2007, as you can see, we are gaining more than the long-term average, the water storage I mean. But in the recent years, some areas in the central side and northern side, we are much losing, we are too much losing the water storage through the time. So as you can see, it is based on the centimeter. For example, 20 centimeter per year we are losing the water storage compared to the long-term average. It's very important information. So now you may have a question how we get export from these maps, because these are really interesting maps. You can use it for your own research and studies. So it's very easy to do. Just you need to use the matplotlib library. Let's call the matplotlib pyplot as plt. plt.savefig. So .save figure, we want to save this figure. So this is, for example, water storage anomaly map. Convert it into a PNG, DPI 360, and BB box inches should be tight, just like this. After a few moments, you will have in the left panel a PNG file that's showing the water storage, easily downloadable, and you can save it on your system. There you go. So let me show the map here. Now you can see it has very high quality, and you can use it for your own study area. So it's very interesting things. That's the power behind of the Earth observation satellites and AI algorithm, thanks to Earth engine and Google system offered for the remote sensing users. And everything is free of charge, and we can use it for all around the world, not limited to one single location. It is applicable or extendable to the rest of the world. I hope you like it as much as I did, and if you faced with any challenge, feel free to share your questions on my YouTube channel, and please share these tutorials with all remote sensing fans in all around the world, because we want to actually improve the capability of the scientists about dealing with Earth observation satellites. Thank you for your attention.